In this, the first video on the law of logarithms, we're going to show you the three laws, show how they're connected to three laws for exponents that you already know. But we're not going to actually do the derivation. The derivation takes too long for the three laws of logs, and they can be found in your locally developed resource. So as mentioned in the introduction, we're going to show the connection between our laws of exponents and our laws of logarithms. Remember that logarithms are just the inverse of exponents. This was something we discussed in our very first video on logarithms. Let's look at one of our laws of exponents. When we multiply powers with the same base, the resulting power has the same base, and the exponent is obtained by adding the original exponents. So for example, a raised to the b times a raised to the c is going to be equal to a raised to the b plus c. So if one asked you to multiply x to the fourth by x to the 3, you would end up with x to the 7. If someone asked you to multiply 2 to the 5 by a 2 to the 6, you'd end up with a 2 to the 11. Now let's look at the corresponding law of logarithms. When you add logarithms with the same base, the resulting logarithm has the same base, and the argument is obtained by multiplying the original arguments. For example, log base a of b plus log base a of c, notice that they have the same base of a, is going to be equal to log base a of b times c. So if you are taking log base 2 of 9 and adding log base 2 of 3 to it, you can do that addition because the logs have the same base of 2, and what you end up with is log base 2 of 27, where 27 is the product of 9 and 3. Similarly, log base 5 of 0.1 plus log base 5 of 34 is going to give us log base 5 of 3.4, where 3.4 is the product of 0.1 and 34. Notice the relationship between these two laws. When you multiply powers, you add the exponents. But when you add logarithms, you multiply the arguments. Isn't this what you would expect for inverse operations? The next law of exponents states that when we divide powers with the same base, the resulting power has the same base, and the exponent is obtained by subtracting the original exponents. So for example, if you had a raised to the b divided by a raised to the c, you end up with a raised to the b minus c. So if you had x to the fifth divided by x cubed, you would end up with x squared, and if you had 2 to the 9 divided by 2 to the 2, you'd end up with 2 to the 7. So let's look at the corresponding law of logs. It states, when we subtract logarithms with the same base, the resulting logarithm has the same base, and the argument is obtained by dividing the original arguments. So for example, we would have log base a of b subtract log base a of c. Notice that the base of those two logs are the same, they're both a's. It's going to give us log base a of b divided by c. So a log base 2 of 21 subtract log base 2 of 3 is going to give us log base 2 of 7. Similarly, log base 8 of 45 subtract log base 8 of 9 is going to give us log base 8 of 5. Please notice the inverse relationship between this law of logs and the original law of exponents. With the law of exponents, when we divide powers, we end up subtracting the exponents. However, with the law of logs, when we subtract the logarithms, we end up dividing the original arguments. Let's look at our last law of exponents. When a power is being raised to an exponent, the resulting power has the same base, and the exponent is obtained by multiplying the original exponents. For example, a raised to the b, which is then raised to the c, is equal to a raised to the b times c. Most of you would know this as the power of powers rule. So if we had x to the 4, which is then cubed, that would give us x to the 12. And if we had a 3 squared, which is then raised to the 7, it would give us a 3 raised to the 14. Now let's look at the corresponding law of logs. When a logarithm is multiplied by a value, i.e. a constant or a variable, the resulting logarithm has the same base and the argument is being raised to an exponent equal to that constant or variable. So c times log base a of b is equivalent to log base a of b raised to the c. So 2 times log base 7 of 4 is equivalent to log base 7 of 4 squared, which is equivalent to log base 7 of 16. Similarly, 1/3 times log base 5 of 8 is equal to log base 5 of 8 to the 1/3. 8 to the 1/3 is the same as the cube root of 8, which is equal to 2. Therefore, we can conclude that all of this is equal to log base 5 of 2. Again, notice the inverse relationship between these two laws. So let's start using these three laws of logs. Our first question asks us to simplify the following logarithmic expressions. I'm going to start by writing down my three laws of logs at the bottom of the screen here so that I have them to refer to as I do the questions. So with question A, I have log base 2 of 5 plus log base 2 of 12 being added together. Because these logs have the same base of 2, I can use my first law of logs and multiply the arguments so that I end up with log base 2 of 5 times 12, which can be expressed as log base 2 of 60. This logarithm has been fully simplified. In B, I have 4 times log base 9 of 2. I can use my third law of logs so that I can express my logarithm as log base 9 of 2 raised to the 4. 2 raised to the 4 is 16, so my final answer is log base 9 of 16. In question C, I have log base 3 of 35 subtract log base 3 of 7. Again, these two logarithms have the same base of 3, so I can use my second law of logs to simplify it. It can now be expressed as the log base 3 of 35 divided by 7. And when that division is completed, I'm left with my final answer of log base 3 of 5. Question D is a bit of a trick question. You might initially think that you use your first law of logarithms to simplify this expression, but that's not the case because the base of these logarithms are different. The base of the first logarithm is 4 and the base of the second logarithm is 5. Therefore, we can conclude that this logarithmic expression cannot be simplified. Question E has 3 logarithms, all with the same base of 6. 2 of the logarithms are being added together and 2 of the logarithms are being subtracted. So we're going to be using our first 2 laws of logs simultaneously. We end up with log base 6 of 8 times 5 divided by 4. And that leaves us with log base 6 of 10. Now question F, which reads log base 5 of 8 plus 2 log base 5 of 3, requires us to use 2 laws of logarithms. I am, however, just going to use the third law in my first step. The 2 log base 5 of 3 can be expressed as log base 5 of 3 squared. And that 3 squared gives us a 9. Now I'm left with 2 logarithms with the same base of 5 that are being added together. That means I can use my first law of logarithms to simplify it further, such that it's expressed as log base 5 of 8 times 9, so that we ultimately get an answer of log base 5 of 72. Now with our next question, we're going to solve 4 logarithmic equations using our laws of logs. With question A, I have 3 logarithms all having the same base of 2 being added and subtracted from each other. That means I can use my first and second laws of logs to simplify it to x equals log base 2 of 6 times 4 divided by 3. Well, 6 times 4 divided by 3 is 8, so now my question reads x is equal to log base 2 of 8. How would I proceed from here? Well, I'd change my equation from its logarithmic form to its exponential form so that it reads as 2 to the x equals 8. So 2 to what exponent gives us 8? Well, the answer is 3. So our original logarithmic expression was equal to 3. In question B, we have 2 times log base 6 of 3 subtract log base 6 of 54. Now, we're going to use two laws of logs here. We're going to use our third law first, and then we're going to follow that up with our second law. The 2 log base 6 of 3 can be expressed as log base 6 of 3 squared, where the 3 squared is equal to 9. Now, when I subtract logarithms that have the same base, I can express them as one logarithm in which the terms in the argument are being divided. That's how I end up with log base 6 of 9 divided by 54 being equal to x. Next, I've reduced the fraction. I've noticed that 9 divides into both the 9 in the numerator and 54 in the denominator, which leaves us with the fraction 1/6. Now I'll change it from logarithmic to exponential form so that the question now reads as 6 to the x equals 1/6. Well, we know that 6 to the 1 is equal to 6. Therefore, 6 to the negative 1 gives us 1/6. Remember that negative exponents mean reciprocals. So we've discovered that our original logarithmic expression is equal to -1. Now, in question C, the unknown x is the base of all three of our logarithms. Since our bases are all the same, we can still apply our law of logs, even though we don't know what the exact value of x is. We're going to use our first two laws of logs because our first two logarithms are being subtracted and our last two logarithms are being added. My equation can now be expressed as log base x of 12 times 4 divided by 6 is equal to 1. When I evaluate the 12 times 4 divided by 6, I get 8. So log base x of 8 is equal to 1. Change that to its exponential form, so it would read as x to the 1 is equal to 8. So x simply equals 8. That's the unknown base of our logarithms in the original question. With question D, we're going to still use two laws of logs. We're going to use our third law first and then our second law. We've taken the 3 log base 3 of x and expressed it as log base 3 of x cubed. Now that I have two logs that are being subtracted from each other that have the same base, I can use my second law of logs. So my next line reads as 2 is equal to log base 3 of x to the 4 divided by x to the 3. When we do the division, we end up with simply x. So our question now reads 2 is equal to log base 3 of x. We'll change this from logarithmic to exponential form so that it reads as 3 to the 2 is equal to x, and therefore x is going to equal 9.